When most people think about risk, they think about it badly. I don't mean they're stupid, they're not. I mean they think about it in a way that feels right, but is subtly, profoundly wrong. And that's worse than being stupid, because a feeling that's wrong is much harder to correct than an idea that's wrong. Here's what I mean. If I asked you right now, what's more likely to kill you, a plane crash or an asteroid impact? You'd almost certainly say plane crash. And in one way, you're right. Planes crash every few years. Asteroids that kill everybody, we haven't had one of those since the dinosaurs. So it sounds obvious. But wait just a second, because here's where it gets interesting. The probability that you personally die in a plane crash in any given year is very, very small. Something like 1 in 11 million, depending on how much you fly. But the curious thing about asteroid impacts, the really curious thing, is that the rare, enormous ones change the math completely. Because when a rock big enough hits this planet, it doesn't kill one person or 1,000 people, or even a city. It kills everybody, or close to it. So when scientists say the average annual risk of dying from an asteroid impact, averaged over all the possible sizes and frequencies of impact, is actually comparable to dying in a plane crash, they're not being dramatic. They're doing arithmetic. You take a very large number of deaths, 1 billion let's say, multiply it by a very small probability, 1 in 1 billion years, and you get a number that's meaningful. That's how probability works when you're dealing with low-frequency, high-consequence events. That's the sneaky thing about risk. It's not just about how often something happens. It's about how often it happens multiplied by how bad it is when it does. And most people only ever think about the first number. Now let me tell you what we know about the history of this problem, because we have evidence. Beautiful, terrible, undeniable evidence. About 66 million years ago, and I want you to just sit with that number for a moment. 66 million years. That's older than the Himalayas, older than most of the continents in their current shape. A rock about the size of a small city came screaming out of space and hit what is now the Yucatan Peninsula in Mexico. It was somewhere between 10 and 15 kilometers across. It was traveling at roughly 20 kilometers per second. That's 20 kilometers. Every second. If you drove at that speed, you'd cross the entire United States in about 4 minutes. When it hit, it released energy equivalent to roughly 100 trillion tons of TNT. To put that in perspective, and I love putting things in perspective because numbers without perspective are just noise. The bomb we dropped on Hiroshima released the energy of about 15 kilotons of TNT. This asteroid released the energy of 100 million megatons. That's not 1 billion times more powerful than Hiroshima. That's 4.5 billion times more powerful. We have to just keep saying the numbers until they start to land. The crater it left, which we now call the Chicxulub crater, is 150 kilometers across, and it's buried under 1 kilometer of sediment on the Yucatan Peninsula. Half of it is on land. The other half is under the Gulf of Mexico. It was discovered not by astronomers looking at the sky, but by geologists looking for oil. Isn't that something? The scar of the worst catastrophe in the last 66 million years, and we found it by accident. Now what happened after that rock hit? The immediate effects were horrible enough. There was a fireball. The rock vaporized. The shockwave leveled everything in a vast radius. There were earthquakes of magnitude 9, 10, maybe 11. We don't really have a great way to measure earthquakes from 66 million years ago, but the geology tells us the ground shook catastrophically all around the world. There were tsunamis, waves that may have been over 1 kilometer tall near the impact zone. Imagine that. A wall of water taller than a skyscraper, washing over the continent. But here's the thing about that impact that really gets me. The truly devastating part wasn't the explosion. It was what happened next. The asteroid hit a region rich in sulfur-bearing rock, gypsum mainly. When it vaporized all of that rock and launched it into the atmosphere, it created an aerosol of sulfate particles that spread around the entire globe. And those particles blocked the sun, not just for a few days, for years. Maybe 2 years of near-total darkness, followed by decades of reduced sunlight. Can you see what that does? You cut off the sunlight. You stop photosynthesis. You stop photosynthesis, plants can't grow. Plants can't grow, the animals that eat plants start to die. And then the animals that eat those animals start to die. The whole food web, which took hundreds of millions of years to build, starts to unravel from the bottom. It's like pulling out the foundation of a skyscraper. The building doesn't fall immediately. It takes a while, but it falls. 75% of all species on Earth went extinct. 75%. We talk about endangered species today. We get upset when a single species disappears, and rightly so. But this event erased 3 out of every 4 species that existed, including, most famously, the non-avian dinosaurs. Every Tyrannosaurus, every Triceratops, every Brachiosaurus, all gone. Not gradually, in geological terms, almost instantly. Dinosaurs had been on Earth for 175 million years. They were spectacularly successful animals. They had survived multiple other extinction events. They had diversified into hundreds of forms, from things the size of chickens to animals 10 times the size of an elephant. And one rock from space ended all of it in what amounts to a cosmic eye blink. Now here's the question I want you to sit with. What did the dinosaurs do wrong? Nothing. That's the answer. They did absolutely nothing wrong. They had no warning system. They had no scientists. They had no telescopes. They had no physics. They couldn't know it was coming. And even if they somehow knew, they had no way to do anything about it. The rock hit, and they died. That is not our situation. And that difference between the dinosaurs and us, is almost the entire point of what I want to tell you today. Let me back up and explain what we actually know about the current threat. Because when I say asteroid threat, I don't want you to imagine something vague and science fictional. I want you to understand what we actually track, what we've actually cataloged, and what the numbers actually say. There are millions of asteroids in our solar system. Most of them live in what we call the asteroid belt between Mars and Jupiter, and they stay there happily and never bother anyone. But some of them, through gravitational nudges, through collisions with each other, through the subtle but relentless pressure of sunlight called the Yarkovsky effect, some of them get pushed into orbits that cross Earth's path. We call these near-Earth objects, or NEOs. NASA and the astronomical community have been cataloging these objects for decades now. As of today, we've identified over 30,000 near-Earth asteroids. Of those, roughly 2,000 are classified as potentially hazardous, meaning they're large enough to cause significant damage, and their orbits bring them within about 8 million kilometers of Earth's orbit. 8 million kilometers sounds like a lot, and it is a lot in everyday terms. But in the context of the solar system, where the sun is 150 million kilometers away, 8 million kilometers is practically next door. It's like saying the person lives in your neighborhood. The good news, and there is good news, genuine, scientifically solid good news, is that for objects larger than about a kilometer across, we've now found more than 90% of them. The really big stuff, the planet killer stuff, we mostly know about. And none of the ones we know about are on a collision course with Earth in the foreseeable future. But here's where it gets more complicated. Objects between about 100 and 1,000 meters. Things large enough to devastate a region or even a continent. We found less than half of those. There are tens of thousands of objects in that size range that are out there, crossing our neighborhood, that we simply haven't cataloged yet. Let me give you a concrete example of how this plays out in real time. In December of 2024, astronomers discovered an asteroid called 2024YR4. It's somewhere between 40 and 90 meters across, roughly the size of a football stadium. When they first tracked it, the calculations suggested it had about a 1.3% chance of hitting Earth on December 22nd, 2032. Now, 1.3% sounds small. You might shrug at 1.3%, but here's how to think about it. If I told you there was a 1.3% chance that a stadium-sized rock was going to fall on your city in 8 years, would you shrug? And more importantly, if there was a 98.7% chance it was fine, but a 1.3% chance of devastation, wouldn't you want to know for certain which one it was going to be? The astronomical community took it seriously. Telescopes around the world tracked it. The James Webb Space Telescope was pointed at it. And eventually, with enough observations to refine the orbital calculations, the probability dropped to less than 0.01%. It was a false alarm, which is the most common outcome, and which is exactly what you hope for. But here's what struck me about that episode. The whole process worked. Astronomers discovered it. The international community organized. The probability estimates updated in real time, and eventually the data gave us clarity. That is the system functioning as it should. Now I want to talk about something that I find genuinely fascinating from a physics standpoint. What could we actually do if we discovered an asteroid was heading for Earth with enough warning? The answer is quite a lot, actually. The key insight is this. In space, you don't need to destroy an asteroid. You just need to change its velocity by a tiny, tiny amount. See, if you can alter an asteroid's speed by even a few millimeters per second, that's barely a crawl. And you do it years or decades before it would have hit Earth. Then by the time the asteroid arrives at the point where Earth would be, Earth has moved. The asteroid misses by thousands of kilometers. A tiny push, given enough time, becomes a huge change in where the rock ends up. This is not theory. This is something we have actually tested. In September of 2022, NASA deliberately crashed a spacecraft into an asteroid. The mission was called DART, the Double Asteroid Redirection Test. The target was a small asteroid called Dimorphos, about 160 meters across, orbiting a larger asteroid called Didymos. Neither of them posed any threat to Earth, but they were perfect test subjects. The spacecraft hit Dimorphos at about 22,000 kilometers per hour, and it worked beautifully. The impact shortened Dimorphos' orbital period by 32 minutes. That was enormously more than the minimum threshold for success, which was 73 seconds. The extra push came from the debris kicked up by the impact, which acted like a rocket exhaust, transferring additional momentum to the asteroid. For the first time in human history, we deliberately and measurably changed the orbit of another body in the solar system. We moved an asteroid. Let that sink in for a moment. We moved an asteroid. A species that 100 years ago was just figuring out powered flight has now developed the technology to redirect objects in space. So here's where I want to bring this all together, because I've been building toward a particular point, and I think you can feel it coming. The dinosaurs were destroyed by a rock from space. That is a fact. It is written in the geology of every continent on Earth. You can find that layer, the KPG boundary, they call it, in exposed cliff faces in Denmark, in Italy, in New Zealand, in North America. A thin band of iridium, the element that's rare on Earth but common in asteroids, laid down 66 million years ago when the impactor vaporized and spread its material around the globe. It's a geological scar of unimaginable violence, and it's everywhere. Now here's what's different about us compared to the dinosaurs. And I want to be very precise about this because I think people often wave their hands at it. First, we know the threat exists. The dinosaurs didn't. They had no concept of asteroids, no way to observe the sky in a meaningful way, no framework for understanding what was coming. We have spent decades systematically cataloging near-Earth objects. We have dedicated telescopes. We have computer models that can trace orbits millions of years into the future. Second, we have the physics to understand the problem completely. We know how orbits work. We understand orbital mechanics. It's just Newton's laws applied to the motion of bodies in space. And Newton's laws are among the most thoroughly tested ideas in the history of human thought. There is no mystery here, no exotic new physics required. The problem is entirely solvable with tools we already have. Third, and this is the remarkable one, we have now demonstrated that we can actually do something about it. DART wasn't just a scientific curiosity. It was a proof of concept for planetary defense. We can hit an asteroid with a spacecraft. We can change its orbit. Given enough warning, and enough means years to decades, not centuries, we could prevent an impact. So the question isn't whether the threat is real. It is. The question isn't whether we could do something about it given enough notice. We could. The only real question is whether we have good enough early warning systems. And the honest answer right now is, we're getting there, but we're not there yet. The objects larger than a kilometer, the true extinction-level threats, we've found most of them. But the intermediate-sized objects, the ones that could destroy a city or a region, we've only cataloged about 40 to 50% of those. Thousands more are out there that we simply haven't found yet. The Chelyabinsk meteor of 2013, maybe you remember this one, came in over Russia and exploded in the atmosphere over the city of Chelyabinsk. It was only about 15 meters across, but the explosion was equivalent to about 440 kilotons of TNT. It shattered windows across a wide area, damaged thousands of buildings, and injured about 1,500 people, mostly from flying glass. Think about that. 1,500 people hurt, not by the rock itself, but by their own windows. That object was not in anyone's catalog. We didn't see it coming. It came from the direction of the sun, which is where ground-based telescopes have a blind spot. It gave us no warning. Now scale that up. A 100-meter asteroid impacts with the energy of tens of millions of tons of TNT. A kilometer asteroid changes the climate of the whole planet. It ends civilizations. Possibly ends the human story entirely. The Tunguska event in 1908. Another one over Russia. An object estimated at about 50 to 60 meters across exploded in the atmosphere over a remote part of Siberia and flattened approximately 2,000 square kilometers of forest. 2,000 square kilometers. If that object had arrived a few hours earlier, as the Earth rotated, it would have been over a major European city. We were lucky. The dinosaurs were unlucky. And the difference between luck and preparation is the only thing I want you to take home today. You know what I love about this problem? It's solvable. It's genuinely, completely, tractably solvable, given sufficient warning. Cancer is hard. Aging is hard. Poverty is hard. These are problems where even our best efforts run into the deep complexity of biology and economics and human behavior. But an asteroid obeys Newton's laws. It follows a path through space that is completely predictable given sufficient observation. The physics of deflection is understood. Hard engineering, yes, but not mysterious. There's a beautiful and slightly tragic irony in all of this. We live in a universe that is, by cosmic standards, violent and indifferent. Asteroids have been slamming into planets since the solar system formed 4.5 billion years ago. The moon, that thing you see in the sky every night, formed when a Mars-sized object hit the young Earth and blasted a huge amount of material into orbit. The craters on the moon that you can see with binoculars are scars from billions of years of bombardment. This is normal. This is how solar systems work. The violence is built in. And for most of the history of life on Earth, there was nothing any creature could do about any of it. A rock comes, you die. Whether you were a single-celled bacterium or an armored dinosaur the size of a house, your fate was the same. You had no say in the matter. But something extraordinary happened when a species evolved on this planet that could understand the universe around it. A species that could look at the sky and not just see pretty lights, but calculate where those lights would be tomorrow, next year, in 1,000 years. A species that could look at a rock flying through space and say, not just, what is that, but where is it going? What will happen if it keeps going there? And what can we do to change that? That's us. We are, as far as we know, the first species in the history of this planet capable of understanding the threat and doing something about it. The dinosaurs had 175 million years on Earth and couldn't prevent their destruction. We've had a blink of geological time, and we've already moved an asteroid. The question that remains, and this is the one that keeps some scientists up at night, is whether we have the institutions, the foresight, and the will to fund and maintain the systems that would give us the warning we need. Because planetary defense is, at its core, insurance. The most rational, cost-effective insurance policy the human race has ever had the option to buy. And right now we're paying for part of the premium, but not all of it. The universe has been throwing rocks at this planet for 4.5 billion years, and they will keep coming. One of them ended the reign of the most successful group of large animals that ever lived. We happen to be the first occupants of this planet with the knowledge and the technology to look up, do the math, and potentially say, not this time, that possibility, that for the first time, a species gets to have a vote on whether it gets wiped out by a falling rock, strikes me as one of the most remarkable facts about the era we're living in. We usually think of space exploration as this grand, outward-facing adventure, and it is. But it's also, quietly, one of the most important things we can do for the survival of everything we care about down here. The dinosaurs looked up at the sky for 175 million years. What they saw, we can only imagine, but they couldn't do anything about what was coming. We can. And to me, that's not just a scientific fact. That's a responsibility.